Hello everyone, my name is Godwin Cece and this is my lab report for Lab 5, the Slinky Drop, in Physics 2211. Getting started, the introduction of this lab. The purpose of this lab is to figure out why the bottom of the Slinky remains stationary even whilst the object is in free fall until the top of the Slinky has fully collapsed. The secondary purpose is to conduct a physics experiment of our choice to follow our physics passion and just pursue something we're interested in. So some fundamental physics principles in this experiment we got are the gravitational force, which is the force equal to the negative mass times the gravity constant, which is negative 9.8. We've also got the drag force, which is force equal to negative the drag constant times velocity. We've also got Newton's second law, also known as the momentum principle, which is the net force is equal to mass times acceleration, or the net force is equal to change in momentum divided by the change in time. We've also got the velocity update and position update formulas, but the final velocity is equal to initial velocity plus the net force divided by mass times time. We've also got the position update formula, which is the final position is equal to initial position plus the average velocity times time. In our experiment, we've got our system, which is a spring, and our surroundings, which is the earth. So this experiment is quite simple. All you have is a slinky that you hold at the top. As you extend down, as it reaches static equilibrium, and then you drop it from the top, and as it drops, the bottom of the slinky stays stationary until the top of the slinky hits it, and then they both fall at the same rate down, as you can see from the tracker data. You can see at the start, the bottom of the slinky remains stationary until about 4 seconds of the slow-mo video. And then after that, it goes down along the top of the slinky, and this is in slow-mo video, not in real life, so some initial conditions are a bit off. As you can see here in the initial conditions, we've got the mass of the slinky is about 1.8 kilograms, and this is just taken from a little bit of a guess and check. We also included the position vector, which is approximately 0, which was taken from the tracker, as well as our initial velocity, which is equal to 0 because the object starts at rest. So this experiment can be put into two separate sections. The first section is where the bottom of the slinky remains stationary due to the net tension force equaling the net weight force, setting this net force to 0, but we've also got the second section, which is where there's no longer tension force and there's only a drag force pointing up acting against the weight force. In this case, the tension force is equal and opposite to the weight force, so the object remains stationary. However, in the second case, the drag force is not equal to the weight force, so therefore the object does start falling down. And in both cases, we got our ball velocity and our ball position update formula all correct. As well as here, when we look in the position update formula, we have to understand to take into account the velocity as well as the change as it goes through the air. Same in this scenario as well. As you can see here, we have graphed out the observed positions of the bottom of the slinky and the model positions of the slinky, and this is over the time of 7 seconds. This is the slow-mo video, not the actual function, because it's easier to figure out the points in the slow-mo video. As you can see, here's all nearly the same graphs and some slight differences, but we'll discuss that in the discussion slide. During the first part of this experiment, the bottom of the slinky had a tension force that was equal and opposite to the force of the gravity. However, when the top of the slinky came down, there was no longer a tension force holding up the bottom of the slinky, so it started falling as shown in the model. And in the video in the last slide, we saw there was some discrepancies in the data, but those can be chalked up to outside forces acting on the system that were not accounted for in the model or in the human errors in the tracker, as well as the experiment itself that messed up the model a little bit in any. But anyways, thank you all for listening and goodbye.